Okay guys, this is the second video on Factorial ANOVA. So we want to look through an example here so you can see exactly how to calculate the Factorial ANOVA. Remember, I'm not going to ask you to do that on the exam. It's just so that you have an idea of what differs between the way you calculate this ANOVA and the way you calculated previous ANOVAs. To preview, there's a lot more in common than there are differences between them. Okay, so the example we're going to work with has to do with memory for false medical claims, particularly, and I guess more specifically how effectively we can debunk those false medical claims. So if you heard, let's say, that eating lemongrass might increase your libido, or drinking ginseng tea might increase your memory, if we found out later that these were inaccurate medical claims, how effectively could we debunk them? How effectively could we get people to reduce their memory for the false medical claims so that they no longer follow that advice but follow the more accurate advice? There's a lot of myths out there that people hold, and some of the purpose of research is really examining whether or not these myths or beliefs that we have do play out in behavior. So one belief that a lot of people have held in the past and probably still do is that individuals who experience mental illness can't work. If you're suffering from mental illness, you surely can't work. You'd have to stay home, you have to recover, and while of course suffering from any illness you should definitely try and recover, that doesn't mean there aren't tons of individuals with mental illness in the workplace all the time. It doesn't mean just because you have a mental illness that you're no longer capable of work, right? Each type of illness needs to be taken in kind, and it may or may not actually affect your work. Another claim that a lot of people will sometimes make is that disasters bring out the worst in human behavior, right? This brings out the worst in people. Anytime it's the worst case scenario, then the individuals perform the worst as well. And I think, as you're actually probably seeing now, and recently, that's actually not always the case. While there are certainly some isolated incidents of people who take advantage, people who gorge on products that are needed during an emergency or a disaster, but for the most part, we see a lot of spontaneous and really generous contributions from our fellow humans. And so it looks like it doesn't actually bring out the worst in human behavior. By and large, it brings out the best in human behavior, with a handful of exceptions, right? So then, to bring us back to our question, how effective could it be to debunk false medical claims, and to what extent might it depend on your age? That is it easier to debunk these claims when they're held by younger adults than when they are held by older adults? The design we're going to use, we'll have younger adults and older adults here. We're going to try two different ways of debunking these claims with just one repetition, saying that no, this is not a real thing and that this is the factual information over here. And then we'll have another group that gets 3 repetitions, right? So they hear it 3 times. So those are 2 completely different groups of individuals, the 1 repetition versus the 3 repetitions. So that independent variable is a between groups, between subjects independent variable. We also have younger adults versus older adults. This again, because it's not being measured longitudinally, we're not measuring the same people again 25, 30 years later in their life. Instead, we're measuring 2 different groups, right? A cross-sectional, not longitudinal study. And so both of these 2 independent variables, age and repetitions, are between groups, between subjects, independent variables. So we have a source table, just like we've had before, and this one is filled in with the actual equations themselves, so you can see that really calculating things is highly similar to the way it was before. With respect to calculation of main effects, for the calculation of age, because of the way we set it up, and I'll go back here, you'll see that age was set up as the rows, younger versus older rows, and then repetitions was as columns. So when I go into here, you'll notice that the subscript next to age, over next to the mean in that row, say between, but it also says rows, right, corresponding to the difference between the rows themselves. And so what the sum of squares there is for that term is saying that the average of the rows, right, and so that marginal mean, but this case for the rows, minus the grand mean squared. We have degrees of freedom, which corresponds to the number of rows, in this case 2, minus 1, so it would be a 1 degree of freedom there. We have a mean square that's done just like before, where we have the sum of squares divided by the degrees of freedom. And then finally we still have F ratios, where we have the mean square of that particular row in the source table divided by the mean square within, and that gives us the F ratio for that independent variable, and interaction. So we see the same thing with repetitions. In order to figure out the sums of squares for the interaction, we do it a little bit differently here, though there are a couple methods. Once you've calculated the sum of squares for each of your 2 independent variables, You also need to calculate the sum of squares within and the sum of squares total, and then you'll find that the sum of squares interaction is simply the sum of squares total minus those other three sums of squares. So just like before, they all add to the sum of squares total. So if you're missing one value, you can always figure out what the other values are by addition or subtraction. We still have degrees of freedom just like before. The degrees of freedom interaction term is taken by the degrees of freedom of the rows times the degrees of freedom of the columns. In our particular example, because both of our independent variables were 2 levels, that means the degrees of freedom for each was 1, and 1 times 1, we'd have a 1 degree of freedom for the interaction as well. The within groups degrees of freedom is a function of how many individuals contributed to each of those cells. So if there were 25 younger adults that received 1 repetition, then you would have a degrees of freedom for that cell of 24, and you'd have to do that for each of the cells, add them all together to get your degrees of freedom within, and then finally degrees of freedom totals, just like it was before, the total number of individuals in the experiment minus 1. Okay, so realistically, the factorial ANOVA is almost identical to the way we've calculated between groups ANOVAs in the past. We just have a couple of more steps because we have an extra independent variable and we have an interaction that has to be calculated. We then have all these degrees of freedom. So it's spelled out over there, but I wanted to give you a little bit bigger version of this. So degrees of freedom rows corresponds to whatever independent variable you placed in rows. In our case, it was younger versus older. That's 2 groups, 2 minus 1. Degrees of freedom columns has to do with repetitions. Again, we had 2 groups, 1 repetition versus 3 repetitions, so 2 minus 1. Our interaction is then the 1 times the 1 there. Our degrees of freedom within, we don't actually know based on the data we've seen so far because we don't know how many individuals were collected in each of these 4 cells, the younger 1, younger 3, older 1, and older 3. And so we can't get degrees of freedom total yet either. We do see that data here, so it looks like if you look at the X column that there were 3 individuals in each of these cells. So there were 3 younger adults who received 1 repetition, there were 3 younger adults who received 3 repetitions, and so on. And so then our degrees of freedom within, if we do go back here where you actually have to take the degrees of freedom of each cell, it would be 3 minus 1 for each of those 4 cells. So it would be 2 plus 2 plus 2 plus 2. So our degrees of freedom within would be 8. Degrees of freedom total then is the total number of individuals in the experiment. There were 3 in each group and 4 groups, so that's 12 minus 1 would be 11. All right, and so it's really easy to calculate these, just like it was before. Nothing's really changed with the factorial ANOVA. Okay, so here are all of our raw data, and we can go ahead and start with calculating the total sum of squares, because with the total sum of squares, we really don't care what groups they're in. So for this, I haven't added any color coding that you're going to see in the next few slides. I've just placed all the data, all of our individual scores, for the degree to which they make errors in remembering the factual information about medical claims. I place those in the X column. All of those are there, even though you can see the groupings to the left of it. We're not worried about those groupings right now because we're just doing total sums of squares. So the total sum of squares is just X minus the grand mean. The grand mean, if you added them all up and divided by 12, was 0.0672. So if we then subtract off the grand mean from each of these, our grand mean was 0.21. If we subtract off the 0.21 from each of these values then, and then square all of those values in that far right column and add them up, we get the sum of squares total of 0.0672. Okay, sum of squares total of 0.0672. So then we really need to calculate the sums of squares for the rows and the sums of squares for the columns to see if we have an effect, right? To see whether or not that 16 is different from the 26 and whether that 21 is different from the 21. To preview, I don't think the 21 will be different from the 21. So I've color-coded this to show that we are really looking now at the rows only. We are not looking at columns, and this is why the young 1 and young 3 are grouped together, because they are both in the young row. And so what we do there is find the mean of all of that row. So if you remember the idea of marginal means, this would basically be like creating the average of all of those individual scores in the young group, regardless of whether they received 1 or 3 repetitions. Their average happens to be a 0.21. As it turns out, this happens to be the average of the older adults as well. So in the yellow, we see the average of 0.21. I'm misspeaking here. 0.16 for the younger adults, 0.26 for the older adults, and 0.21 is still our grand mean. So for the younger adults, because if you add 0.25 all the way down to 0.16 and you divide by 6, you get an average for that row of 0.16. The other group, you add the 0.27 down to the 0.26, you get an average of 0.26. Okay, so those are our 2 means for our rows. The sum of squares between says that we take those data and we subtract off the grand mean. So I note that we're using the same mean value for the row in all 6 of those lines in blue. The 0.16 appears in each line. The grand mean never changes either. So in all 6 lines, you're doing 0.16 minus 0.21 and then squaring all of those values. You're going to do the same thing then for the other set of rows, the 0.26 for the average of older adults minus the 0.21, which is the grand mean. And then square all of those values as well. Once you've squared them all, if you add them all up together, you will get a sum of squares for that row of 0.03. Apologies, my neighbors have an asshole dog who never shuts up. My sweet dogs are actually wandering around the backyard corner. Okay, we also have to talk then about the sums of squares for the columns, right? The effect of repetitions here. And so we're going to color code these differently as red and green. Notice the marginal means here of 0.21 and 0.21 taken by averaging over those 2 cell averages in each group, the 0.20 and the 0.22, the 0.12 and the 0.30. Right? And so now we want to see whether these two are different from one another. They're not likely to be different from one another. And so again, just like before, for all the individuals in the 1 repetition and 3 repetitions, that's where we're looking now. And so we take the 1 repetition group where the marginal mean was 0.21. We take the 3 repetitions group where the marginal mean was 0.21. Turns out they're all 0.21 minus 0.21, so it really doesn't matter in this case. But you subtract all those off, square all of those. Of course, it's a whopping 0 because 0 squared is still 0 and 0 summed is always 0. So you get 0 for the sum of squares for this particular set, or this particular independent variable, 0 for the sums of squares columns. Okay, now we need to look at the sum of squares within so that we can then subtract off to get our sum of squares interaction. So the sum of squares within is the individual scores minus the mean of the individual cells. So the average of the young ones would be 0.25 plus 0.21 plus 0.14. That comes out to a 0.20 average, and so for all 3 of those, you take the x minus that average. 0.25 minus 0.20, 0.21 minus 0.20, 0.14 minus 0.20. Move down to the young 3s and now use the average of that cell, the 0.07 down to the 0.16, subtract those off of each of those scores. Do the same thing for each of your other cells, finding the average of the individual cell and then subtracting it off of the raw value for each of the scores in that cell, right? Those give you your deviations, then you need to square all of those deviations, you need to add all of those up, and for these data that would give you a sum of squares within of 0.018. We can then, using our source table and using all the formulas we have within it, now calculate the last few values that we have missing. So we did not come up with our sum of squares interaction, but we do have the sum of squares for our rows, our columns, our within, and our total. We already know all our degrees of freedom, and so if we plug all of our values in then, and compare them then to our critical value, remember we always need a critical value for our hypothesis test. In this case, we still have between groups degrees of freedom, so you're going to have a critical value that may differ for each different term, different independent variable. If you have an independent variable that you're testing that's 14 levels, then when you test that independent variable, your critical value will be different because the between groups degrees of freedom will be 13. In this case, both of our independent variables were 2 levels, so it works out easily. We have the 1 between groups degrees of freedom. We also know then that our within groups degrees of freedom was 8. Right, and so the 2 folks there are 3 people in each cell, 3 minus 1 for each cell, 2 plus 2 plus 2 plus 2, and so our cutoff value for these particular data is a 5.32. But remember, if one of my independent variables happened to be, let's say if age was very young, old, and very old, right, and I had 3 groups there, then when I was testing my F ratio for that particular row for the age, in this case what was rows for us, I'd be using the 2 between groups degrees of freedom to find my critical value, and so I'd go over 1 to what looks like a 4.46, I believe is what's underneath that arrow. So again, it's depending on what your particular term is. In this case, you'll notice that our degrees of freedom for each of our terms here is 1, and so we're always going to just be using the 1 and the 8. And so anyway, if you solve across there, you find that your sum of squares for the interaction comes out to 0.0192. If you then solve across the table by taking sums of squares, dividing by degrees of freedoms to get mean squares, you find all these 4 mean square values. To find the effect of each of your independent variables, you have to take the mean square in that row of the source table and divide it by the mean square within. And so for the F ratio corresponding to the main effective age, we take the 0.0300 and divide it by the 0.0023. This gives us an F ratio of 13.04. This was well beyond our cutoff value of 5.32, and so we would say there is a difference in how effective it is to debunk false medical claims between younger adults and older adults. If we look at the effective repetitions, our F ratio is 0. This is nowhere near passing our 5.32 cutoff, and so we do not have an effect of repetitions. It appears in our data, at least, that the number of repetitions of the debunking information of false medical claims does not have an effect on either younger or older adults' ability to forget those medical claims. And then finally, the interaction. Is it possible that we can debunk the medical claims in either group, but it only takes, say, 1 repetition for younger adults and it takes 3 repetitions for older adults? Or might it have opposite effects where repeating things over and over again to one group actually makes them remember the false information potentially even better? Right? So again, any effect could be in there. We see with our F ratio of 8 that we do have a significant interaction term, and so we need to figure out what the interaction term means, because it basically is telling us that the effective age is not the same at each level of repetition, or the effective repetition is not the same at each age. And so either way, let's see if we can figure that out. If we look at our data here, we actually plot the averages for each of those 4 cells. What you see is that when you're looking at younger adults, when you repeat this information, their error rate does considerably go downward, right? And so they no longer are continuing to repeat the false medical claims. They do so at a significant rate when they only have 1 repetition of the factual information, but with 3 repetitions of the factual information, this does reduce their error rate. For older adults, by contrast, this goes the opposite direction. Repeating the factual information actually increases their error rate. Now, we'd have to examine why this could be the case. It may be that in the repetition of the factual information, it also tells you about the counterfactual. So it says something like, have you ever heard that ginseng could help your memory? Well, it turns out that it can't help your memory, and it's possible that the older adults are only remembering the first part, and upon repetition, it's making that first part even more memorable. And so they're not actually getting their false information debunked. Instead, it seems to be strengthening that. That could be one interpretation of this interaction, but we need the graph here in order to really look at the data and see what might be going on. And so again, the cool thing about between groups ANOVAs, and the cool thing about multiple independent variables here, not between groups ANOVAs, factorial ANOVAs, is that with multiple independent variables, we can see how one variable may act very differently in the presence of another variable. The way that repetitions affects younger adults is very different from the way it affects older adults. So you can't really just say there's an effect of repetition that always increases error rate, because in one group it increases it, in the other group it decreases it. You can't say that repetitions have no effect on error rate, which is what you would say if you average those 2 increase and decrease effects, because it clearly does have an effect. It just depends on whether or not those repetitions are being delivered to younger adults or older adults. So we've talked a little bit about effect size, and it's worth it while we're still with these data to discuss how you would look at the effect size of a factorial ANOVA. Remember, we use R squared to look at ANOVA effect sizes, and so we use sum of squares divided by other measures of sums of squares. And so in this case, if we wanted to look at the effect of the rows themselves, we simply take the sum of squares rows as the numerator, and then the denominator, which stays the same in all 3 of these, is going to be, the first 2 of these, is the sum of squares total minus the sum of squares column and the sum of squares interaction, right? You're essentially getting back to what's left then, which would be the sum of squares rows, and you're partialing it out to see how much of the overall variance is due just to the rows. You do the same thing down below then, swapping out the rows for the columns in the denominator and the columns for the rows in the numerator. So when you're looking at the effect size of the independent variable that corresponded to columns for repetitions, you do the sum of squares for that, divided by sum of squares total minus those other 2 sums of squares. Finally, we have the sum of squares for the interaction term that gets involved in the effect size for the interaction term. So sum of squares interaction over sum of squares total minus sum of squares rows minus sum of squares columns. Remember that when you get an effect size, they tend to be fairly small numbers, and so Cohen gives us some metrics for determining how large our effects really are. In behavioral sciences, we would say that if your R squared is between 0.01 and 0.06, then you have a small effect size. If it's between 0.06 and 0.14, you have a medium effect size. And if it's above 0.14, you definitely have a large effect size. So I told you at the very beginning that ANOVAs could handle really any situation. We talked about it handling multiple independent variables and variables that could be different types, manipulated between subjects, manipulated within subjects. We also see that it can handle situations where you add in another variable, but you're really not interested in its effect. You're interested in removing its effect from the data. In this case, you're adding what's called a covariate. So maybe you wanted to look at the effect of repetitions, but you didn't want to look at the effect of age. You wanted to remove the effect of age from your groups. And so you, instead of actually putting it in as an independent variable, you enter it, as a covariate. And when you enter it as a covariate, you're allowed to remove its effect, right? In the same way that we talked about with partial correlations a long time ago. And so if you have a covariate, then you are in the world of an ANOVA. You can also look at multiple dependent variables, looking how they both get affected in similar ways or different ways by those independent variables. So maybe you wanted to look at memory and you wanted to look at reaction times. In this case, you have multiple independent variables, a multivariate analysis, and we have a MANOVA. And then finally, you could even have a multivariate analysis that had a covariate in it as well, and then you've got a MANCOVA, right? And so really, once you've got the ANOVA design, as long as you can meet those basic assumptions, then you really have a design that can handle almost any data you can throw at it. The one thing we have left to really talk about in this class is what happens when you do really break a lot of these assumptions. What sorts of tests do you have left that are non-parametric, right? All these tests are parametric tests. So this lecture is about what the ANOVA is really in its larger size, this factorial idea, how we can look then at both main effects and interactions because we have multiple independent variables. That introduced the idea of sums of squares and degrees of freedom for rows as well as columns, and then the interactions in the cells in between. And then finally we wrapped up by looking at a measure of effect size for factorial ANOVA.